Hello, my name is Gavin Baker, and today I'll be talking about circuits. So the purpose of this lab is to use energy conservation to predict the behaviors of various wires and currents. Now I will explain what concepts support these observations, and later I'll explain the data and sort of like the reasoning and the physics behind it all. So for the procedure, I use the circuit conversion kit online to create various circuits and methods for analyzing them. They involve batteries, resistors, volts, and more. There were some major changes in the voltage at some points, like with the capacitors discharging and charging, and many interesting observations. It was pretty fun playing with it. So, connecting the data and the physics, our main physics concepts that were used were the loop rule, the node rule, V equals I times R, and C equals Q divided by V. For the loop rule, it states that the round trip of the electric potential is equal to 0. If you go all the way around, you're going to get back to the same spot. And the node rule states that this current into the wire is the same as the current out of the wire. So you have current going in. If it splits up and then comes back together, that current will be the same due to energy conservation. So here are some of my data and measurements, my calculations by adding up all the electric potentials using the loop rule and figuring out, simplifying the parallel and series to solve the problem and figure out the current. And I made sure that my calculations match with the circuit conversion kit, and they did. So here's a graph of how voltage reacts over time. At the beginning, it's at 0, it's uncharged, and jumps way up to 3 volts after hitting the battery. And it keeps steady until it hits a resistor, and then it starts to decrease, hits another resistor, goes down again, and then it goes down again at the ammeter, and then goes steady, and eventually it will approach 0 due to the loop rule. Here are 2 capacitors. One is charging and one is discharging. And they're very similar. With the capacitor, where it starts uncharged and it slowly gains current, which eventually causes the light bulb to dim. But when it first starts, it causes the light bulb to shine really, really brightly. And when the battery is removed, the light bulb also shines really brightly due to the capacitor releasing its charges out to the light bulb. But it also, over time, loses that current, and the light bulb dims once again. So here is a graph using the equations from earlier, using like the rate of change of Q and rate of change of R. And these are just like the standard equations. It's been linearly adapted to fit this graph. And I calculated earlier that RC is equal to 0.1612. So here's some hypothetical what-ifs. The measure of the current would have been even lower in real life due to resistors being more stronger, more realistic than the simulation. And I think the charger for the capacity would charge more quickly in real life as well, due to the strength of the battery. And the model and the graphs confirm this prediction. So it would have been an overall more realistic approach to do the lab in person versus using the current kit conversion. Thanks for watching.